Well, there's a very long step between the partial pressure suit, which has been shown before, and this particular suit you see now.
A human walking on the moon was the most iconic part of the 20th century, the most iconic moment.
What if the ancient ones that they talk about in a future galactic civilization was us?
So we're trying to move beyond these individual molecular indicators of life on an exoplanet.
And 1 century you spent on Jupiter would correspond to 1 century plus 1 minute on the surface of the Earth.
Retro, go. Fido, go. Guidance, go. Control, go.
Some people think that it would be the end of religion. It might be exactly the opposite.
Consciousness and life might actually spread between the stars and perhaps between the galaxies.
We tend to think of spaceflight as a modern thing, from the 1960s, late 50s, 60s onwards. But actually, we can go right back in time, and we can look at some of these incredible stories about how we imagined we might have left the planet. This is a William Blake picture, which I absolutely love, and I think nothing sums up better our desire to explore and leave the planet than this particular picture. And you can see you've got this young child, I suppose, climbing this ladder to the moon. So that was 1793. That was the kind of how we might get to the moon. I don't know, build a massive ladder. Technical challenges with building a huge ladder to the moon. If you want to go into space, you're going to need some kind of vehicle. So the real sort of proto rocket that I like is this one. This is 1648. L'Homme dans la Lune, The Man in the Moon, written by Bishop Francis Godwin, about a lunar mission that he imagined using geese that would pull you to the moon. These migrating geese, which he called Ganza, migrated from the Earth to the moon. Again, some technical challenges with that one. A little bit later on, the 19th century, of course, writers like Jules Verne imagined things like giant cannons that you could put a sort of capsule with astronauts in a giant cannon and fire them to the moon. And of course, you've got the problem if you make it to the moon, like in the famous Georges Méliès film, how are you going to get back? It seems to be a one-way mission. But actually, that Jules Verne story, From the Earth to the Moon, inspired the rocket scientists that actually developed the real rockets that have taken us to space. People like Robert Goddard, Wernher von Braun, Hermann Oberth, the kind of the godfathers, if you like, of rocket science in the early 20th century. So there you go. We tend to sort of recycle old ideas and add new technology and make them better. But ideas, they don't come from nowhere. They tend to come from behind us. And there you go. Just a couple of, on the right, you've got the Apollo capsule. That's the capsule that took astronauts up to the moon and back down again. And on the left, the Orion capsule. We're going back to the moon. Project Artemis in the next few years will be returning humans to the moon. But you can see how similar they are. The most efficient way of designing a spacecraft is that. And that's why you see so much similarity between the past and the future. Clothes. One of my big interests is the history of the spacesuit, which has a fantastic and fascinating history. I'm really interested in clothes generally, technical clothing, how they're made and where they come from. And the spacesuit is a wonderful example of that. I've got a little video I want to show you in the last sort of few minutes of before we went to space, what we thought spacesuits would be. But actually, this particular film pretty much sums up how a spacesuit works, even though it's a silly video from, I think it's 1957, this particular video. But it's a good example of where we started in our quest to leave the planet.
Just how big a step forward is it? Well, there's a very long step between the partial pressure suit, which has been shown before, and this particular suit you see now. Perhaps we can have this inflated and you can see the action. See, space is a vacuum and the suit has to be pressurized.
But I can see you seem to move around all right. Were you uncomfortable? You're sweating furiously now, but were you really uncomfortable in it?
I was a little hot. I think the reason there is that if you are hot and you don't get sufficient ventilation, then of course, you just sweat and get even worse.
So there you go. That's a good lesson for anyone watching this who's planning on leaving the planet. If you're testing your spacesuit, don't wear a shirt and tie, I think is the lesson from that. But even in sort of 1957, we understood the basics, the science of what a spacesuit needs to be. Obviously, your spacesuit is going to be dependent on where you're going and what you're doing. But ultimately, a spacesuit is a wearable spacecraft of the smallest possible dimensions. This was spacesuit number 1, Wiley Post spacesuit. So you can see, again, the principles of it just being an inflated bag of air. We knew that from spacesuit number 1. And we had some crazy designs along the route. They also designed spacesuits for animals. Here's a Russian dog spacesuit, which I'm rather keen on. And the only cat that went into space, Felicette, and her little friend Hector the rat.
You could ask yourself whether the landing of the moon and watching a human walking on the moon was the most iconic part of the 20th century, the most iconic moment. There was something particularly important, I think, about the moon landing because it made us realize we were not just always going to be on this planet. It gave us a sense for the first time that we could actually exist, maybe live, but certainly we could be on another planet, another part of another world. And we'd already got this growing sense of ourselves from the Apollo missions. You remember this famous photograph, Earthrise, which was taken by Bill Anders on Apollo 8. And the nice thing that was said about Apollo 8 was they went to discover the moon and they found the Earth. Because famously, they were just preparing to go into moon orbit, and suddenly looking out of the command module, Anders saw this beautiful scene of the blue globe, the blue planet rising there. They rushed to get a camera, they photographed it, and then everybody back on Earth suddenly understood what they understood, how incredibly remote, but also how incredibly fragile our situation was. And it was a way of seeing ourselves that we hadn't had. We could imagine it, but we hadn't actually seen it. We understand a problem like the problems now of climate change and the environment, but to be able to perceive for yourself the problem, to be able to actually clap eyes on it, that's really special. That does move minds and hearts and changes things, I think. And as we said, it was a mass participation event. It was estimated there were about 500 million people watching this event across the world. And of course, it all got going, it got ramped up and it got fast when Jack Kennedy made his very famous speech setting out the challenge, which he made on a university campus. And the beautiful thing that's often neglected is the rest of the content of that speech. We all remember the famous line, "We choose to go to the moon not because it's easy, but because it's hard." But look at what he's saying here. He said, there is no strife, no prejudice, no national conflict in outer space as yet. The hazards of outer space are hostile to us all. Its conquest deserves the best of all mankind, and its opportunity for peaceful cooperation may never come again. That idea of peaceful cooperation in the space race is often thought to be rather ironic and not entirely sincere, given that we know that Kennedy and many people in the administration were motivated by a technological race against the Soviet Union, with the idea being if we showed in the West that we had, technological proeminence, this would be defeating and running down and eventually ruling against the idea that there would continue to be a nuclear arms race that the Soviet Union could compete with us in. But that's not actually what happened. I don't know how many of you know this, but at the stage in '62 where Kennedy was making this speech, he actually asked Khrushchev, do you want to come in with us on this? Do you want to join us in trying to land someone on the moon? And Khrushchev said, we will take them there, you bring them back. And that wasn't how NASA saw it. NASA knew the hardest thing was to come back. They knew that the Soviets probably had the technology to go there. But also Khrushchev was doing a calculation, and he thought, it's not in my interest when I want to show the strength and the prowess of the Soviet Union. It's not my interest to go in with the US here. But Kennedy was interested, and he asked not once, but twice, to the Soviet Union to join. And this idea that it's because space is hostile to all of us, it's a challenge to all humans, somewhere where there isn't even conflict. This is very prescient. I think the whole speech is very prescient. But he knew that this required a great deal of support from the public as well as from the politicians. Here's the thing you have to remember. Again, it's a moment. The landing on the moon, the Apollo mission, it was publicly funded. This wasn't about private commercial interest. This was a publicly funded, publicly supported project run by and with the help of many public institutions. But also what the moon landing represents 50 years on was one of the greatest ever management projects that's ever been achieved. Publicly funded project using more than 53 universities, using the technology of many people in the public sphere and the people in mission control. And the people in mission control, you don't really necessarily know what they do because they have these technical terms. So the flight controllers are all responsible for particular things, for the retrofiring of the rockets coming back, for the flight dynamics, for guidance. And many of you have heard that very famous piece of audio when you've got Gene Kranz going around the room. He said, I'm going to go around the room and I want a go, no-go decision on whether we go for landing, whether or not we descend to the moon. And he says, retro, go, FIDO, go, guidance, go, control, go, telecom, go, GINSI, go, econ, go, surgeon, go. If any one of them had said no go, it was off, it was finished. All of that work, all of that money, it would have been over. So let's return to this moment, the giant leap for mankind. Wonderful thing that Mike Collins said is everywhere they went, they were toured around in India, in Africa, in Latin America, in Europe. They were toured around, the astronauts, when they got back. And Mike Collins said, people rushed up to us and said, we did it.
So I think life on Mars would be challenging, but I think we could survive on Mars. And the reason we could survive is because we've found water on Mars. So I think in the future, Mars might be a destination that many humans would be making. Now, the thing is, what would people find on Mars? You could live in biodomes, you'd need spacesuits to go out. But one of the things, or one of the ideas in science fiction is the idea of terraforming. And I must admit, I love that idea. It's the idea of taking sort of a barren world like Mars, and slowly but surely you could heat it up, melt some of the water. You could get asteroids from the asteroid belt, which is right next door, drop water onto the surface. You could heat it up using solar sails, pointing sunlight onto the planet. And if you could get enough water and heat it up, you could actually make Mars a lot more like Earth. But what if you want to go further? Well, sometimes people ask me, you build big telescopes here on planet Earth. Why are you putting things in space? Space missions are incredibly expensive. The sort of space missions I've worked on have been of the order of sort of £300 million. So $300 million actually, about that order. And that's not including the launch costs. So why do we put them in space? Well, the answer is this. We put them in space to get a better understanding of what's out there. This across here, this is a graph showing the electromagnetic spectrum. The electromagnetic spectrum is the only form of energy that can travel large distances of space. So down here we've got radio waves, millimeter, infrared, visible. These are all sort of wavelengths that we can detect. Up here we've got UV, X-ray, gamma rays. Up that end we're getting to the real high power stuff. X-rays and gamma rays are the sort of things that can really disrupt our DNA. And down here we're actually looking at what can penetrate through our atmosphere. So radio waves happily travel through our atmosphere, and that's why we can send radio signals across the Earth. Millimeter waves, we get most of it through. Visible light. When we actually think of astronomy, we mainly think of visible light. We see stars. We see the light coming from them. But if you look at X-rays and gamma rays, this radiation doesn't actually penetrate our atmosphere, and this causes us a problem. But actually, it's quite beneficial as well. X-rays and gamma rays they can cause leukemia. When we send astronauts up into space, they go above the atmosphere, and suddenly they're bombarded with radiation. Astronauts have spent a year on the International Space Station, and one of the biggest challenges is keeping them safe from that radiation. The radiation fluctuates. Sometimes we have something called a solar maximum. Every 11 years, the sun goes through cycles of activity, things called coronal mass ejections, which are the size of planet Earth hurtling into space. And also we have solar minima, where there's not so much solar activity. When there's a solar maximum, lots of X-rays, gamma rays, these sort of hard radiation is coming and hitting our Earth and hitting people in space. And so when that happens, they need protection, otherwise they get leukemias and cancers and things like that. So we're really very lucky that X-rays and gamma rays don't penetrate our atmosphere. But at the same time, if they don't penetrate our atmosphere, it means that we can't observe here on planet Earth things that are giving off X-rays and gamma rays. And I always like to compare it with a picture by Van Gogh. This is a picture called Starry Night by Van Gogh. And if we look at it in its different colours, it's really hard to see exactly what's happening. We can look at it in the blues, we can look at it in the yellows, we can look at it in sort of the green hues, and it's not until we put everything together that we get the complete picture. And it's exactly the same with our sun, or the universe around us. This is our sun seen in visible light. We've got a few what we call sunspots, but effectively the sun looks quite benign like that. But let's look at the same sun in UV, extreme UV, X-rays, I think radio waves. It's not until we put all these images together that we get a much more detailed view of the sun. Looking at it in just one band doesn't give us the complete picture. We need to put all those different wave bands together to get the complete picture and see what's happening.
But no, we have the technology, we have the rocketry, as Kieran mentioned, we've had people in space for a year. Okay, we'd have to stay for 2 or 3 years, but that's probably not an insurmountable problem. Going to a different solar system is orders of magnitude more complicated. So to get there in any sort of human timescale, you would need to travel at a speed 1,000 times order of magnitude faster than what you would need in order to get to Mars. Now, to travel 1,000 times faster means that you have to pump into your spacecraft 1,000,000 times more energy per unit of mass that you want to take. So we're talking about a technological challenge which is orders of magnitude greater than what Elon Musk is trying to solve. And if you're interested in coming back, how the hell do you come back? You have to find some way of obtaining energy there and pumping it into your spaceship so that you can come back again. And I think that's another, to my mind, very, very difficult. I'm not going to say insurmountable because old professors should never say that anything's impossible. So maybe we should give up on the idea of sending people. And maybe we should just send DNA. Now, first of all, let's send our DNA. But what's the point of sending our DNA? Because when our DNA gets to the other end, even assuming we could stop it once it got there, what's it going to do, right? So, what we should be thinking in terms of is some sort of elementary DNA building blocks, which we'd have to package in extremely sophisticated ways so that it would survive the hazards of interstellar travel, radiation, collisions with other dust particles, and so on and so forth.
There is a project called the Breakthrough Starshot, financed by a Russian-American philanthropist, Yuri Milner, which is about using lasers to accelerate light sails with small, stamp-sized microchips on. So the idea here is that within a few decades, hopefully, if everything works out, we could be able to send them at 20% of light speed. It's not going to be an enormous starship with a lot of space cadets on it. It's just going to be a fairly stupid piece of software, but you can send a lot of them relatively cheaply. And I do think that if we go to the stars, it's not going to be humans going there first. It's going to be our software and our robots, and we're going to start out with really small ones. But then you can use that to build a foothold in our solar system, a big radio receiver to get further instructions, solar panels, convert that to a habitat, and maybe take that DNA that you carefully sent in some of these stamp-sized probes and start cultivating a biosphere inside that habitat, and eventually get humans there.
What I wanted to say with respect to Mars is, first, we cannot survive on the surface because there are cosmic rays that would damage our body. We will need to get to caves underneath the ground. And, we started in prehistoric caves to protect us from the rain. And we might actually end up, if we ever go to Mars, in caves. But in terms of putting humans in space, it would be much better to build an artificial platform, because you can then choose the distance from the furnace, the sun, as it changes over time, the sun will brighten up and you just want to choose the optimal distance from the furnace or build your own nuclear reactor. We shouldn't rely on existing bodies just because nature made them. If we go to space, let's make our own habitat.
But you're talking about changes that are billions of years in timescale, or hundreds of billions of years in timescale. We have to take first steps, and the first steps should be achievable within, political timescale.
Yeah, so the space station, if you read the news, existed. And all I'm talking about is another space station that provides humans with a much better habitat for them to sustain normal life on that. Rather than going to Mars, have a space station that supports us in a better way.
As you may know, and you see maybe the tent at the very end, we are very much involved in development of the ExoMars rover. This is really led from the UK for the rover itself. It's like a laboratory on wheels, going to Mars and explore, search traces of life. It's been fully kitted out with a suite of instruments, and also for the first time, we'll have a 2-meter drill that will be able to probe the ground and to go, in a layer that we think is hospitable, favorable for current and past traces of life, potentially. There's always a communication delay with Mars between 3 and 21 minutes one way. So you can't really operate it like real time. And this is why we embed a lot of autonomy into these platforms, these rovers, to perform complex operations without the need of an operator. So in terms of actually exploring all these different environments, first thing is you have to survive. And if you look at the long list on the right, there's lots of things that could really prevent you from doing so. First, you have to survive the launch shocks and vibrations, radiations, both on the way to your target and actually as you operate there. Thermal extremes, say between like -200 to +100 degrees on the moon. And of course, whether you're actually operating in vacuum or with an atmosphere, whether there is dust that is corrosive, that is magnetic, and so on. And you could, depending on destination, come across liquids, such as the oceans on Europa or methane lakes on Titan. So all of these different environments will actually drive the design of these explorers in terms of material selections and, of course, how you operate them. First of all, you have to survive the landing. And this is where I kind of hand it to Kerry to talk through the landing system.
Thank you, Elie. We are providing the autonomous landing, a component of the autonomous landing system for this lander, which is being developed by Airbus. And what we are providing is a LiDAR. A LiDAR is kind of like a radar, but using pulses of light instead of radio waves. So our instrument will send pulses of light to the surface and measure the time for this to come back to the instrument. And then we can use that to measure distance. And as we scan the pulse of light across the surface, we can build a 3D map. And this is run through software, and we try to figure out where the safest place is to land. So green is a safe area and red is not safe. So we perform one scan at around 2 kilometers. The lander's moving at around 17 meters per second. And we scan an area around 300 by 300 meters, which is the equivalent of 9 football pitches. And we perform this scan in 5 seconds. And then based on this, the lander will retarget and aim to the safest spot. It will continue its descent. And then at 200 meters, it will perform another more high resolution scan. And once again, it will look for the safest area to land. We have to try and take into account a lot of challenges when we're designing for space missions. So vacuum, high ranges of temperature. Part of the way we do this is we do a lot of testing on the ground. So you can see on the screen, we've performed tests at very long runways to make sure that we can actually correctly identify safe areas. We've also used the LiDAR on a robot arm, which simulates the conditions of the lander as it's descending. So we shake it around a lot, and then we generate scans like the one on the right to make sure that we are correctly selecting a safe landing zone. We also have to be very careful that we select the right materials to ensure that things like the optics are not degraded by radiation, that the electronics are not going to stop working in different temperatures or in vacuum. So to talk a little bit more about the material side of things, I'll hand over to Stephen.
Thank you. My name's Stephen Kyle-Henney. I'm Managing Director of Titix Limited. we make advanced materials. So most people are familiar with carbon fiber, very strong, very stiff. Well, we do the same sort of thing, putting ceramic fibers into titanium or aluminium. Very, very strong, very stiff structures, ideally suited for space missions and space environments. So we've been doing a lot of work at making pressure vessels and fuel tanks for space systems, parts for aircraft, landing gear, and through making the tubes for landing gear, we got the opportunity to work on robotic arms. So we've done a number of programs with Airbus and with Ellie. The main one that we've been doing is one called the LARAD project, which is a large arm. So this arm here, designed to lift quite large loads for its size in a space environment. We did some very clever things here. We made the arm in one piece. We added some 3D printed. Everyone's heard of 3D printing, hopefully. So where you use metal to melt metal to the direct shape of the final part. That was made by one of the partners on the program, and then we bonded it directly to our tube to give us the stiffest, lightest structure we could possibly manage. And then Ellie and the rest of the team built that up into a robot arm. So challenges of space for materials are, it's very expensive to get into space. So between 10,000 and 50,000 per kilo you put into space. That's really expensive. The Mars missions are at the upper end of that, lunar missions are at the upper end of that. So you want to take out as much waste as possible. And that's where our materials come in. The other thing is it's very, very harsh environment. There's lots of radiation, so you need materials that won't get damaged by radiation. There's a lot of heat change, so minus 100 degrees to plus maybe 200 degrees. That's really quite challenging for materials because they'll expand and shrink at that temperature. And you don't want sensors like the LiDAR being 5 millimeters out, because that's a big difference at 2 kilometers if you're picking a safe landing site. So our materials are very stable. Ceramics in them keep them very stiff and very stable. So we can do lightweight materials, we can do net-shaped materials that make them easier to make, lighter to make, and more robust for the final part. And you end up with arms like this, which are about as compact and about as light as you could possibly make to fit inside a spacecraft and land on the Mars or on the Moon.
We also have lives worth living, and there could be so many more lives worth living if we actually spread out. So right now, the surface of Earth, the biosphere, is a very, very thin layer. The total mass of the biosphere is, of course, by a normal individual human standard, tremendously vast, but is a tiny fraction of the mass of Earth. Indeed, if we rolled up the biosphere and all the water in the ocean and put them together, you would get a globe about the size of Spain, I think. Again, on an individual human standard, that's a very, very big globe. But compared to Earth, it's tiny. In fact, there is more water on many of the moons of Jupiter. So suppose we went to space and started to learn how to mine asteroids, to convert that metal into space stations, took the ice and the organics and turned them into soil and planted the gardens and had animals and humans. How much more space would there be for humans and the biosphere? And it turns out that it's several million times more. You can scale it up, and indeed, if you start using the outer planets as raw material, now we're talking billions and trillions times more. It gets into these vast numbers that are simply inconceivable. There could be so much more future. And I'm still just talking about the solar system, which is a fairly modest solar system. The Milky Way got 300 billion stars, give or take. Some of them also much more long-lived than the Sun. I love to point out that although I like the Sun a lot, as a G2 star, it's kind of a fuel-inefficient star. It's not going to burn all its hydrogen. It's going to burn out in just about 5 billion years. While some of the small red dwarf stars you can see with a good telescope, they're going to run for trillions of years. Yes, they sputter a bit with flares and have other inconveniences, and you need to have a planet orbiting rather far in, and some of you might not like the aesthetics of a red light, but they're the little Volkswagen Beetles of the universe. They're gonna keep on going for a long time. So I think we might also want to go there because we want a big open future. We don't really know maybe what the meaning of life is, but we're going to need a lot of time to find that out. We're also going to need new experiences. And I do think deep down we also need this optimism that there is an open future. That doesn't mean that we should say, yeah, there is a planet B, so we can totally skip caring about Earth, because most of us will never leave Earth anyway, because it's going to be darn inconvenient to get into space. And most of us are going to say, yeah, I'm not going to give up my little village. But some crazy people are going to do that, and we should be very thankful for those crazy people. Some of those crazy people are our ancestors who climbed down over trees or went out of Africa. And most of the sensible monkeys in the tree said bye-bye. And hopefully, of course, we can say bye-bye to the crazies, go off to Mars and later on to the stars. And then we should actually look forward to a really big open future where consciousness and life might actually spread between the stars and perhaps between the galaxies.
So the new reason to do this isn't the beauty of gazing into the night sky or man's quest to know his place in the universe. If we don't figure out how to spread out, we are running one single experiment with godlike powers and the wisdom of morons based on our current political leadership. There is no way that this terminates well. Furthermore, there is no faster than light travel inside of general relativity. So you can look up at the night sky and you can know more or less that unless you're betting on time dilation and other exotic effects and wormholes, we aren't going anyplace. There are only 3 habitable spheres. Now, the world's richest people, 2 of them, Bezos and Musk, are focused on rockets to get us into space. One of us thinks that we can diversify with 3 spheres. The other seems to think that Gerald K. O'Neill's circular space stations with artificial gravity are the way to go. Bezos actually makes more sense. Neither of these make much sense at all. And the odd thing to say, and again, I don't want to go too much into social commentary, is that if we could only get physics to be vaguely phallic in shape, load it with high explosives and oxidizers, we could get fully funded, and I think we'd probably have a theory within 20 years. At the moment, nobody seems to be motivated on the idea that you break it, you bought it. Physics has a ton of social responsibility. We unleashed this power. I encourage everyone to read Edward Teller's letter to Leo Szilard at the end of the Manhattan Project, and to reevaluate their theories of Edward Teller. His idea was that war had to become so unthinkable that we could never have another. And 75 years of this peace have dulled our sensibilities, forgetting that nuclear weapons have not gone away, and we've added biologicals. If we're not very careful, we are going to have to go farther through the valley of death that physics has led us into if we are ever to escape, diversify, and have some hope that some of us at least will make it in the long term. And in fact, I would say we have an obligation. I think Teller's comment was to tie the toe of the genie from the bottle we helped it to escape. If the theory of everything exists, it renders Einstein and the Standard Model as effective theories to be deduced from the underlying theory. We don't know whether an analog of the prohibition on faster than light travel persists into a lower layer until we have such a theory. So it could be that if you had the theory of everything, you could prove that you will never meaningfully escape the solar system.
So I'm doing something very shocking now. I'll actually agree with Eric, which is that I think physicists totally underestimate their responsibility, and I think the relevance of the foundations of physics at this point in the history of time is totally underestimated. We need some new technologies. We're kind of running out of ideas here, and I think they have to come from the foundations of physics. Now, where we start to disagree is exactly where those new ideas should be coming from. And I don't really think that quantum gravity is the right direction to look. I've worked for a long time on quantum gravity. I don't think that looking for mathematical consistency is the right thing to do, but we should be looking for experimental evidence. And I can talk about this for some time. But the point is that all those effects of quantum gravity, they're like really, really small. And even though I think they're super important to understand the universe, I can't really see that they're going to be technologically relevant in the near future, which is why, as of recently, I'm more working in the direction of the foundations of quantum mechanics, where we're talking about the measurement problem, because quantum mechanics is the theoretical framework that underlies all our current technology. And if we understand this better, if we figure out that this is not fundamentally the right thing to do, that's going to impact all our technologies and is almost certainly going to lead to applications.
If the human race became a multiplanetary species, what consequences would this have on ourselves and our place in the universe? Big one there for you.
Wow. As an analytic philosopher, that's a hard one to answer. I don't think we know what consequences that would have. We were a multi-spacefaring, and that's far in the future, by the way, I think. We would have to be different. We would have probably genetically modified ourselves so that we could tolerate maybe greater exposure to radiation. And our bodies are designed to basically live on Earth. And that's a big problem. Even on Mars, it has lighter gravity, but even on a space station, you're going to have to, it's very unlikely you're going to be able to get a space station that provides us with all the things that we need to survive and last very long. So I think genetic engineering would happen, and who knows how they would engineer us. I mean, who knows what we would be like if they were engineered. Some people think that it would be the end of religion. It might be exactly the opposite. People would become more religious. It's very hard to predict that, except to say that to become a spacefaring species, I think we're going to have to become different physiologically.
Interesting. What would you have to say about that? Multiplanetary species, how will it change us?
So it's not inevitable that it'll happen. So Avi likes the idea of exploring space because of the neighbors we'll meet. I find it more inspiring to pursue that goal if there are no neighbors, because I see that as an enormous responsibility. Like, what if the ancient ones that they talk about in a future galactic civilization was us, right? What if we really are early? And what if life is very rare, then I think it's a dire responsibility to not die on this rock. And I think there is a serious risk of us dying on this rock. And I think the way to get off the rock isn't to put people on Mars in 20 years. I think the way to get off this rock in the right way is to work towards that as a long-term goal. What happened when people left Africa and spread around the world? We created many, many warring nations and tribes. It'll be much worse in space, where the generations-long light travel time means that there is no communication. We will have to change for every planet that we're on. We'll adapt, and we'll adapt ourselves, and we'll become many different species.
I think there's a couple of very big moral questions which I think have been posed, but let's just pose them again in a particularly clear manner. So one is, do we have, in some sense, a moral responsibility to try to preserve as long as possible life as we understand it? On the other hand, do we have a moral responsibility to avoid snuffing out life that may exist somewhere else? If we, for example, send a probe to one of these moons of Jupiter, and if it carries, some of our bugs, are they going to snuff out the bugs that are already existing there and prevent, their monkeys from descending from trees 100 million years hence? Supposing we go to Mars and the probes are already looking for life, and supposing they find some extinct life form on Mars that could be resurrected. Should we try to resurrect that life, or should we just leave it?
So we know, for instance, that we can think of how the Earth affects its environment and affects the motion of the moon around itself as the Earth curving the fabric of space-time, and then the moon, for instance, traveling along straight line in this curved geometry. Now, because it curves the very fabric of space and time, it doesn't just affect space as we seem to be representing in this picture. This is just my inability of showing you a curvature of time, but the curvature of time is very present. And you can see it, for instance, if you compare how your clock ticks on various planets of the solar system or various objects in the solar system. If you are on Earth or if you are on the moon, the gravitational field from the Earth is different from the gravitational field from the moon, and therefore the way your clock would tick on the moon and the way that it would tick on the Earth is different. Would actually grow slightly older, you will actually grow older slightly quicker on the moon than you would do on Earth. So if you spent 1 century on the moon, that would correspond to 1 century minus 2 seconds on Earth. If you compare the gravitational field from Jupiter, for instance, which is much more massive, to that of the Earth, it means that you would feel time go faster on Earth than you would do on Jupiter. And 1 century you spent on Jupiter, on the surface of Jupiter, if you could do that, would correspond to 1 century plus 1 minute on the surface of the Earth. So that's starting to be a more noticeable difference. Now, if you push that to the extreme, it is true that if you're very close to the vicinity of a very massive black hole, 1 hour close to a black hole could correspond to many centuries, or many years at least, living on the surface of the Earth. And so you have this relative notion of time depending on where you are in the universe and close to which gravitational field you are, or how you get accelerated to get there.
And the two scenarios I'm going to talk about are life on exoplanets and also looking for life in the solar system. And both are viable options for these kind of new approaches we're developing. So one of them is looking for, complexity in the solar system, basically. So you have targets like Enceladus, which is a moon of Saturn, that has an ocean underneath the surface. But people are very excited about Enceladus as a target for astrobiology because it actually has these geysers that are spewing jets of water and organics into space. And Cassini actually did flybys of these, so we know there's organics there. And so there's been a lot of proposals about going back to look for signs of life in those plumes. And one way we can do that is actually by using this molecular assembly or molecular complexity measure, or looking for properties of the networks, the scaling behavior of the chemistry, or some of these other statistical properties to try to actually look for signs of life. But molecular assembly is actually measurable in these molecules with a mass spec you could fly. So we have hopes that you could do that. You can also think about Titan, which is another moon of Saturn that the Dragonfly mission is going to be going to. And again, if we want to go and look for life there, we could look for high molecular assembly molecules as a potential indicator that there is an evolutionary process happening on Titan. And also Venus or Mars. These measures are agnostic to targets, so we can use all these things at any target in the solar system that you want to use, that you can get this particular instrument called a mass spec to. Exoplanets are a little bit more challenging because they're obviously very far away. These are planets orbiting other stars. And part of the problem with trying to understand exoplanets is that so far, most of them characterized are Jovian worlds because they're large, Jupiter-like planets that we can get, higher resolution spectra to study their atmospheres. We haven't really gotten that far with terrestrial worlds, which are rocky planets like Earth. We're just starting to get into the era of characterization of their atmosphere. And part of the problem there is we just get a couple pixels of data. So that's what's kind of represented by this little fuzzy picture. And then you have to basically infer all the properties you want to learn about that planet from these couple pixels of data. And so what we're trying to do, sort of as leading the way into these more complex systems and physics-based approaches to life, is develop these assembly theory approaches and these kind of thinking about these patterns in the chemistry that life uses as things that we can try to infer from the data we get from exoplanets. And so that's sort of the next phase in development. But the idea that you want to think about sort of the simplest concept there is not looking for oxygen on an exoplanet, which could be a sign of life or not, depending on that planet. So people have traditionally wanted to use oxygen as a biosignature because it's in our atmosphere on Earth because of photosynthesis. But as people study that more, oxygen is very easy to produce abiotically. If, for example, you have a global ocean and some UV light, you can break apart those water molecules and make oxygen in the atmosphere. So we're trying to move beyond these individual molecular indicators of life on an exoplanet into a suite of molecules and the patterns that they have, and developing this as a tool for inferring life not based on the presence of a single molecule, but a complex pattern that is indicative that there's a living biosphere on that planet. And so just to conclude, this is another one of my favorite quotes, which comes from Erwin Schrödinger, another famous physicist who thought much about the problem of life, and in fact wrote a very famous book called What is Life?, which at the end of the book, which was published in 1944, wrote, "Living matter, while not eluding the laws of physics as established up to date, is likely to involve other laws of physics hitherto unknown." And so when I think about going out into the universe looking for life, I'm actually thinking about looking for these other laws of physics that actually explain us.